Well, I think it started promptly, so Friday before a holiday, it's good of all of you to show up. It's challenging. No, I wanted to, I'm afraid I've been belaboring a little bit on the black body radiation because I think it's a key thing, because this was the start of quantum theory. On the other hand, it's not so easy to explain, even with the math, which you could go through. It's not terribly obvious. So I'm trying as best I can to give you a kind of a feeling for why the black body radiation led Planck to the idea of the quantum. And it follows, you got to put it in the time and place. This was around 1890, 1895. So it's roughly 30 years after Maxwell. And a few years after Hertz was the first to create electromagnetic radiation, man-made, deliberately, and transmitted across the space. So this was a very big deal, and it was in the minds of the physicists of that era, including young Einstein as well. Einstein was born in 1879, so he was roughly 20 years old in 1900. So this was a very impressive thing, the Maxwell theory. Seems to be in very high volume today. So that what they knew is what you know, namely that oscillating things, to get electromagnetic radiation, you needed an oscillating something, charges accelerating. And the easiest thing, and Hertz did it, and others did it, Marconi was working on his antenna to send radiation across the Atlantic, and radio was just beginning. So it's not surprising in a way that when Planck knew about the experiment on the black body, namely that you had an object which was sort of a hollow thing with a hole in it, and out of it came electromagnetic radiation of all kinds. Again, I've showed you the spectrum many times, maybe I'll go back to it again in a moment. But the point is I want you to sort of put yourself in Planck's mind. And electromagnetic radiation was coming out of here, and as I said, presumably they had like a diffraction grating in those years, just in those years, they were learning how to make very good diffraction gratings, and they could spread the colors out and get the full spectrum, even invisible light. Even if you couldn't see it, you could put a grating here, and then you could put some kind of a heat detecting thing at a certain angle, and say, okay, I'm at this angle from the diffraction grating, so I know the wavelength. And so I can figure out how much radiation is coming out of here at that angle, and let's say I make the thing black, so I absorb all the radiation, and I measure the temperature rise of this thing. I can tell how much energy is coming out at a given wavelength. And you can plot that spectrum of the energy per second in that frequency range as a function of the, well, as I say, in those years they're using gratings, no doubt, and so you would plot it as a function of wavelength. So let me even not say frequency. I would prefer they had done frequency, but they did wavelength, no doubt. And so you can plot out at each wavelength, along the angles here, you could plot out how much energy was coming out, and they got this curve. And so the, and they found that, for example, as you, this might be a high temperature, and then if you lower the temperature, let's say quite a bit, you would get maybe this curve, where it's lower everywhere, pretty much, and the peak shifts over. So you have a lambda sort of max here at the high temperature, and you have another lambda max here at lower temperature. This would be T2, and this might be a T1. And as we said, it's not, you know that as you heat things up, they sort of change the glow that comes out of it. The hotter it is, the bluer it is. So that was all known, and this is the quantitative statement of that. But you see, the problem was that there was a theory that said that for every, so here's what I imagine Planck had in his mind. He said, look, there's electromagnetic radiation coming out of the box. I know that electromagnetic radiation is caused by oscillating dipoles or an antennae of some sort. So the fact that there's electromagnetic radiation coming out of the box there must be a little oscillator someplace that are creating this radiation. That's reasonable on the basis of what we know and what he knew. So he said, okay, let me imagine the box is made up of these oscillators. What does an oscillator look like? Well, it might be a mass with a spring, two masses, and you have a spring in it, it vibrates. And if this is a plus and a minus, it'll go like this, and you'll have an oscillating dipole. And depending on the frequency or the stiffness of the spring here, you know, it'll be different frequencies. The frequency inverse 2 pi times the frequency. I think you did this in AA already. Square root of that spring constant over the mass. So depending on how stiff the spring is, you'll get different vibrations, frequencies. So the fact that you were getting out radiation of all these wavelengths suggests that there must be, or at least you can imagine, there were oscillators of all these different kinds of frequencies in the walls. And the temperature, or the heat motion, which he also knew there was heat motion, because that was a theory of kinetic theory, also been developed roughly about 1850 and 60. So you have this heat motion shaking the oscillators. They have their natural frequencies. When they oscillate, by Maxwell ideas, they will radiate their characteristic frequencies, and that's what we see coming out of the box. Seems very reasonable. So his model for it is all these different kind of oscillators in the walls of the box. So that's why it's, although when I said it last time that there are oscillators in the walls of the box, you say, what is he talking about? Oscillators in the walls? What is that? Well, on the basis of the Maxwell theory, that's a very reasonable kind of model, because that's what creates electromagnetic radiation is oscillators oscillating at their frequency. And in fact, there must be the fact that you're getting any wavelength you want, or any frequency you want, you know, that to make the thing even hotter, the curve will go up even more. It seems like whatever I do, I can always make another shorter wavelength by just making it hotter. So there must be all kinds of oscillators in that box, making up the box. It's a very reasonable kind of model when you come to think of it, knowing what he knew and what we know. And so, good as far as it goes. But the real question came in. So this is what I'm trying to say in this slide. I did not put, I just made this up over since Wednesday because I realized I hadn't really spelled out the model very well. Namely, that this is what we knew at the time. That heated bodies emit the radiation up to very high frequencies. There's no limit. They keep going. As high as you can make it, you'll always get a frequency. Very high frequencies. But we know that the radiation is emitted by dipoles. So you model the walls of the black body as oscillating dipoles of all frequencies. Very, very plausible. But by equipartition, every dipole gets the same amount of energy. And that's the trouble. That's where the theory fails. Because if that were true, then when I got to, see, here this is low, short wavelength, or in a way, high frequency, down at this end, right? You see, if every oscillator, if I warm the box, and every oscillator gets the same energy, as if you remember I shook the balls in a little box, and everybody got the same energy, more or less. Now, everybody in these walls got the same energy. I should see high-frequency oscillations at every temperature. Then even if I cool the thing down, I know there are high-frequency oscillators. If I raise the thing high enough, I can get high-frequency oscillators. And if I lower the temperature down to here, they go away. But why do they go away? They should be there. And because everybody gets some energy, it should never be possible that I get rid of them entirely. So the problem for Planck was, why don't you get high-frequency oscillations? when you cool the thing enough, they go away. And you know that the box has the oscillators because I can make them oscillate if I go high enough in temperature. So you know they're there. The question is why when I go to low temperatures, I don't see them anymore. And according to the general theory, I'm shaking the box enough to excite them to some degree. So it shouldn't be possible to make it go away entirely like that. That's the problem. In fact, there should be even much more than here, but they're just not there. There should be a lot, and there's none. So you have a very bad contradiction there. And that's what Planck set out to show, to explain. And the way he said it was, okay, I'll grant you that you're putting in thermal energy. Let me make it with this chalk here. I'm putting in a certain amount of, let's say, energy. And I'm putting in at a given temperature thermal energy. Now, how is it possible, as I'm varying the frequency, that these high-frequency oscillations don't occur when I'm giving them energy, supposedly? So that's his problem. And what he said was, well, it must be that those oscillators at high frequency need more energy than I'm giving them. So that the energy they need maybe is too much up here. So that the energy they need is up here. Whereas I do get the low frequency ones, they're okay. So maybe they just need less energy. And so I can, when I provide this much, they're happy, they go. But when I put in too little energy, they don't. So what he said is that the higher frequency, this is almost funny, okay, the higher frequency ones need more energy proportional to how their frequency is. Because somehow when I put in this much energy, they just don't get going. So it must be that the high frequency ones just need more energy. This is how much energy they need to get going, proportional to their frequency. And that's why at a given temperature, say this low temperature, there's just not enough energy in this frequency range. The energy needed in this frequency range is less than is provided by the temperature. So that makes Planck's guess, his idea, a little more plausible, I think. You agree? I don't know. Does that help at all? All right. When your head's going in circles, I don't know. It tells me maybe not entirely, but okay, we tried. But that's the point. So the real question is, as I said, the point is, again, if you plot this as a function of frequency, as I do here on the right side, if the normal ideas were working and all the oscillators were excited, you would get the curve, you see that going up to infinity, where it says toward the ultraviolet catastrophe. See, as you go up in frequency, not only the modes should get excited, but there in fact are more of them, turns out. And so you should need more and more energy when you go up to the high frequency. Now I'm plotting as a function of frequency. But in fact, the curve turns over and you get no oscillation, very little oscillation. In fact, it dies out exponentially according to that formula there when you go to high enough frequency. So the argument is, as Planck, and this formula that Planck came up with relies on the fact that the energy, h times frequency, is here. When h times the frequency is large, meaning when this is large, compared to the energy you're putting in, which is kT. kT is this whole Boltzmann constant, which I should have talked about a little bit more. Well, this is sort of the energy provided per atom. That's the energy provided. This is the energy the oscillator needs. When kT is much less than hf, the formula says e to the hf over kT minus 1. So when hf is greater than kT, this is a number greater than 1, so it's an exponential to a number greater than 1, so it gets to be a big number. So for hf greater than kT, get this by k here, I'm k Boltzmann, not that k Boltzmann. See, that becomes a number greater than 1, so e to the hf over kT is a big number, because that's a number bigger than 1. So it's like e squared is 10, and so I can forget the 1, and what I get then is hf over e to the hf over kT. And that's a pretty big number. So it says that the amount that's emitted goes down as e to the minus hf over kT, which is smaller. So the energy emitted goes down exponentially as the frequency goes up. So that's the shape of the curve as Planck would have it, this part out here on the right. That's what happens when the energy of the thermal energy is much less than what's needed by the oscillator. And it fit the curve precisely. And from this curve, from the data that he had at the time in 1895 or 1900, somebody had already measured the curve. He fitted the curve very well, and he got out a value for h, because you don't know what h is yet. But you fit to the curve, and you figure out a value of h. And so that's the drift of the next slide. That is to say, it fits the curve very well when both in the region where the energy needed is low, at low frequency, and your energy levels are like this, and you have plenty of thermal energy to excite these things, and so it fits the curve well on the left side of that of the curve, and it fitted the curve well on the right side of the curve. So Planck must have been relatively happy, although he was a rather severe man, and very hard on himself. He didn't really quite understand why this was happening, and he was very unhappy with the idea. And you should be too, in a way, because you learned that the energy of a wave, the energy of something was usually proportional to some squared quantity. Like the energies typically that we've seen so far, half mv squared for kinetic energy. We have a half kx squared for a spring constant. We've had the energy in the electric field is sort of like, was it E squared over epsilon naught, something like that, in an electric field. And we had the energy in a magnetic field was something like mu 0 b squared. Always the amplitude of something. All those energies have to do with the amplitude of a speed, of a distortion, of an electric field, of a magnetic field. Frequency hasn't appeared yet. And he's saying, wait a second, the energy is somehow proportional to the frequency. It made him feel very bad. It should make you feel bad. It makes me feel bad. Because I spent a lot of time learning that, and all of a sudden he's telling me something very different. Something that didn't appear at all. Suddenly I have to worry about the frequency. Because I thought the energy was how big or tall the wave is, right? That's how big it is. Like if a water wave comes in, I care a little bit about how frequently it hits me, but I really care about how tall it hits me. And now all of a sudden he's saying, forget about how tall it is. It's the frequency that counts. It's a big shock. And he didn't quite understand it, and he struggled with it. And we'll understand it from the point of view that well, Einstein finally figured it out, actually, how to look at it, as we'll see. But this is part of the difficulty of understanding what he did, what a big break it was with the past. First of all, Well, it said that an oscillator doesn't oscillate at every possible, see, if this is the energy of the oscillator, but its energy can only be proportional to F, then, or it's actually it's n times that, what it says is that given the frequency of the oscillator, and this is a constant, and this is a number, that means that x can only take on certain values. But suppose this is just some number. Then x can only be a number. And if I make n equals n plus 1, x must, again, adjust itself and only be a different x. So what that's saying, strange thing, the thing can oscillate and have one distortion, and then at the next level, it can't go a little bit more. It has to go to a next more to give me the next level of energy. So it can only have this much of a vibration, well, that much, but it can't be sort of in between. This is the quantization idea. Very, very strange. And we know enough to be puzzled by that. But in those years, but it explained everything very nicely. And, well, here's an example of, again, if you require that you need a certain amount to stay alive, and the heat energy is not enough, it simply dies off. And so you get this kind of a curve, where at high frequencies it dies off, where it shouldn't have died off, because there are oscillators there. Why aren't they going? Well, it just isn't enough to get all the way up, to get up to the shelf that it needs. Again, it's like throwing a bunch of balls up there. Once in a while some will go, but most of the time you simply can't get the ball up onto that shelf, and so it doesn't get populated. That's what quantum is doing. And so Planck said that the energies must be multiples of the frequency, and it fitted very well, and he gets this number, h is 6 times 6 times 10 to the minus 34. It's a very small number, actually, for what you multiply the frequency by to get the energy in that wave. I also point out here that the units are energy times time. Energy is like m v squared. V is a length over time squared, so L squared T squared, but I multiply by time again, so I get rid of one of the T's. And so this is what the units are. I just point this out. It's and then you can call that mL times L over T. L over T is a V, velocity. So this is like a length times a momentum. A length times a momentum is angular momentum. Right? A length times a momentum is what we call angular momentum. L cross P. The length, the units of length is angular momentum. I just point that out because it will turn out that in quantum theory, angular momentum also is in quanta of h. And h has the correct units for angular momentum. And electrons going around atoms, Planck says it, and Niels Bohr used it very importantly to say that the angular momentum is also in these quantized units, also a big breakthrough idea. Okay, so then I try to say more about why it is. And I also talk about the effect. I think, frankly, the atmospheric greenhouse effect is a very dramatic example of black body radiation. Okay, so I hope that's good enough. I hope that we understand that pretty well. Now the next idea was young Albert in the miracle year of 1905, where Einstein did I find it pretty remarkable, actually. He wrote 4 or 5 very good papers in the year 1905. As I mentioned, he was born in 1879, and so he was roughly 25, 26 years old. That was a good year he had then, 1905, a vintage year, where he showed his theory of relativity, where he showed that Maxwell's theory of light, that light is a wave, is universally true, that it doesn't even change if you move with respect to radiation. The velocity of light of this wave will always be c, so that Maxwell's wave equation is true in every inertial reference frame. So he proved very strongly that light was a wave. And then he goes on to write another paper in which he says light is a particle. so I ask, Albert, which is it? Make up your mind. Well, he says, in fact, it's both. So he has it always. And what is he saying? Well, he says something like, he took Planck very seriously. He said, okay, if you have a box, and you have all these oscillators in the box, and these oscillators can only have like h times their frequency, or 2h times their frequency, and they're making transitions between these levels, and they're emitting their frequency by making transitions, what's doing with the light that comes out? See, and instead of saying, as we've been saying up till now, that the energy in the light is proportional to the amplitude of the wave, this E squared, he says, no, let's take Planck seriously, and let's say the energy in the light is proportional to its frequency. And that's the energy of the light. Now, if you feel bad, if you went ahead and learned all that, now you have to unlearn it. If you feel for the rest of the physics community when he said this. So, and he said, but with this idea, he can explain some experiments which up to that point were unexplained. Namely, something like this. What you do, let me try to get the demo. Well, it's this one here. I hope it's this one here. Let me see where it went. Oh, here it is. Yeah, now what he is doing is you have a light here, so if I can turn it on. Intensity, okay, when I turn it on. Here we go. Can you all see this? Is it right to turn out do I need to turn out the lights? Can you see it's okay?